What I'd like to do now is talk about the actual failure properties of steel, especially for wide flange shapes and the like. Steel is kind of a unique material in that we utilize the elastic range for our normal loading conditions and the plastic range for our extreme loading conditions. And this allows us to keep the material costs a little bit lower for our typical loads, but ensure that we save lives if extreme loads are met, meaning the building won't fall down. However, we don't want to over design the beam and the columns, the steel structure for just our normal loading conditions. So what we want to do is talk about the design curve, what this tends to look like from a failure standpoint. So what I want to do is give a stress strain curve. We've actually seen this quite a bit. So the general concept behind this shouldn't be terribly new. However, you'll notice that the curve we've used previously was quite curvy. And anytime you're dealing with curves in mathematical equations are a little bit hard to describe. And so the folks who have put together the design process for steel design have come up with a simplified curve. The elastic portion of the curve still remains very much the same. It's already linear. So we'll label that as the elastic range. However, once we hit that yield point and the material starts to fail, we're going to notate that as capital F sub y, which is the yield stress. For 36 KSI still, the yield stress would be 36 KSI. For 50 KSI still, the yield stress, the point at which it yields, would be 50 KSI. And so this becomes the actual yield point that we're dealing with. Once we cross that yield point, we note that the behavior of the material changes quite a bit, and we start to get some permanent deformation with the material. And so we call that the plastic range. Now, previously, this is where the curvy portion was introduced, but for the sake of simplifying this curve, designers have approximated this to be a linear range as well. And so we end up with this plastic range that exists. The point of strain, remember strain was that Greek letter epsilon, y for yield. This would be the yield strain that's associated with that yield point. For steel, the end of the plastic range, or the plastic strain, is approximately 15 times the value of the yield strain. And of course, at that point in time, the particles and fibers realign themselves such that we start to get what we call strain hardening, and we actually pick up additional strength, but we would have this terrible deformation of our material. So this strain hardening range, and then we tail off with the ultimate strength, the highest value of stress that can be reached for this particular material. Now, we've talked about LRFD, load resistance factor design, that we use for steel in a separate video, but we should note that this LRFD design process is rooted heavily in inelastic behavior. In other words, we're grounding our design process in the plastic range of the curve. So just to quickly recap here, for normal loads, we want to be working in the elastic range of the curve, and for extreme loads, we want to be working in the plastic range of the curve. Extreme loads would be like earthquake loads and heavy wind loads, things like that. What I want to do next is go back and look at the bending stress distribution that occurs. You'll recall that if this was the side of the beam right there, you'll recall that our bending stress looked like this, where we had a peak value of bending stress acting up along the top edge of our curve. Of course, it'd be the same at the bottom edge as well, but this is the actual stress. And anytime that you're within the elastic range, the yield stress profile would look like this. However, there's a maximum point when you actually reach right here at the yield stress. That would be the greatest value of yield stress that you could achieve, and where the curve started to look like this. And the moment that the bending moment that causes this yield point is known as the yield moment right there. So this occurs at yield stress. Now think carefully. Once that yield stress is reached at the upper edge of the curve, you start to experience plastic deformation where the material starts to deform and it can't carry any increased load. But just under the top edge, you haven't reached the peak value of yield stress yet. And if the load continues to increase, what happens is we start to get this permanent deformation. We reach this maximum yield stress value because we can't go any higher than that. But we start to get this permanent deformation that starts to creep into the center of the beam. And we'll just go part way like this for now. Notice that this permanent deformation starts to creep inward. And this is at some point where our M, our moment, bending moment, is greater than the yield moment that caused the diagram at left, the peak bending stress distribution within the elastic range. So what's happening here is the top part of the curve, and of course the bottom part as well, the extreme edges creeping inward have reached a plastic deformation state where they can't carry any additional load. But the interior portion of the curve is still at a stress value somewhat lower than the yield stress. And so it hasn't reached full plastic potential yet. So the top part of the curve is starting to deform. The interior of the curve is not achieving permanent deformation yet. And the bottom part is just like the top part, it has achieved it. There becomes a final, got to notate this real quick. This is greater than the yield. Eventually what happens if the load continues to increase is we hit a point where the entire beam goes to a plastic deformation state. And we get a curve, a stress distribution where the yield stress has been reached at every point along this curve. At that point in the curve, we call that the plastic moment. M equals the plastic moment. Not the yield moment, which is just before the material starts to permanently deform, but the plastic moment where every particle along that interior section has reached a plastic deformation state. This is considered the failure limit for a still beam or a still column. At this point in time, the column cannot carry any more capacity you've utilized the complete plastic range that's available. Everything will start to go to strain hardening at that point in time, which is a good thing because the structure will still carry load. But at that point in time, you've reached the maximum load possible that this particular steel member can handle.